Hey everybody, welcome to another video. So last time we looked at Euclidean patterns. If you haven't seen that video, you don't really need to watch it to do this one, but if you want to, it's going to be up above. What we're going to do today is MCify this thing so that basically instead of having just one sequencer here, you can have as many as you want that run in parallel. And this doesn't, the design that we use here will be able to work regardless of how you generate your patterns, whether that's using a Euclidean algorithm or some other means. So yeah, let's get into it. And before I go into the MC side of things, I actually want to talk just briefly. I realized after doing the video last time that there's a way better way to handle this poly mode thing, where we can control whether the pattern is playing back polyrhythmic or polymetric. So let me show you that really quickly. So I'm going to pull the rate object completely out. It's going to go away. And let's just move all of this stuff over here. And by the way, if you want this patch, it's in the GitHub. I'll put the link down below. It's also in the description of the other video. And then I'm going to de-encapsulate this. Command-Shift-D. And so the thing I realized is we don't need the rate object because this prob feature of subdiv is smart, and it will actually wrap around the probabilities around however many subdivisions you have. So in this case, we're telling it the subdivision is 8, and we have 8 items here. And the way that we were controlling polyrhythmic versus polymetric was to change the length of the incoming phaser. However, if I were to say, subdiv 12 or subdiv 16, it's smart enough to understand that when it gets to the end of this list of 8, it should just go back to the beginning. So that means is that in order to control for polyrhythmic versus polymetric, all we have to do is change what the subdivision is, where if it's polymetric, the subdivision is going to be what we tell it the global subdivision should be, independently of the number of steps in our Euclidean pattern. And if it's polyrhythmic, then the number of steps in the Euclidean pattern will dictate getting this. Let me just delete this stuff for now. Will dictate both the length of the Euclidean pattern and the subdivision. So what we can do is just combine those two numbers. And we want 0, the default, to be polymetric, and 1 to be polyrhythmic. And we can use a ZL-nth, which is just going to take the first item of this list and then pass in the toggle +1. So, and we also need a TBI. So if I send my subdiv, I send my steps, and then I toggle my poly mode, I'm switching between what that subdivision should be. And if we play things, and I set it to 8/8, so just play every event. If I enable, or if I disable, if I go to polymetric mode, then I get a subdivision of 16. If I go to polyrhythmic mode, then I get a subdivision of 8. Now, the whole question of polyrhythm, polymetric, it doesn't really make sense if we only have one pattern, really, because it is something that is really about how different patterns interact with one another. So that's where we get into MC and actually having multiple of these generators running in parallel. So let's actually get into that. So I'm going to delete most of what's here. I will leave this part, which is the actual Euclidean pattern generator. And we'll kind of start from scratch here. So I could have left the phaser and all that. We're going to need that. And now what we're going to do, instead of just using subdiv tilde, we're going to use mc.subdiv tilde, and we're going to have 8 channels. And let's just set a default subdivision of 8 just to give ourselves something. And if we create a mc.scope, we can visualize this result. So we have here 8 channels, and you can see they're all the same because we are just setting globally for all 8 of these a subdivision of 8. Okay, and so now we can do something like, say, prob, and let's just do this in a very basic way to start. If we just connect actually from our Euclidean generator, we can influence globally all of the generators, all of the 8 sequences. So here, because we're just sending this simple message prob and then the sequence, we're just doing it to all of them. However, if we wanted, which we do, to control these separately, what we can do is use mc.target object, pass the sequence that we want to modify into the right inlet, and then the data that we want to send to that into the left. And I'm actually going to set this back to default for now, and then I'm going to delete this connection and add this connection. And I'm also going to go over here into the inspector and just set the inactive channel alpha to 0. All this does is control when you, for all these 7 channels that we're not viewing, whether those are faintly visible when I am viewing any other one. And so if I say, okay, for channel 1, let's use 8.3. You can now see we're getting that, and if I switch to channel 2, we still have 8.8. So if I do, let's do the synceo here on channel, the triceo on channel 1, on channel 2, we'll do the synceo. Beautiful. Cool. So that's that. We can even, if we go to channel 3, use, say, 9 and let's say 5. So now we actually, on the 3rd channel, have a 9-step Euclidean pattern. And so let's do our same thing with the poly mode. So if we create a number box and call it subdivision, and we do that same thing. So we need the ZL nth, pack II. We're going to pass this here. We're going to pass this here. ZL nth 1. Toggle +1. And a TBI. Great. And this, so we want probably this to be global, right? This is kind of a global setting, this poly mode, as is the subdivision. Oops, I zoomed in. So we don't really want to set these on a per sequence basis. So what I think we are going to need to do is actually store the number of steps, or even let's just store maybe, I guess, let's store the parameters for each of our patterns. So we're going to say, we'll create a call called patterns. And I'm just going to embed it in the pattr so it's easier for us to use later. And I'm going to update our Euclidean generator here so that we use this second outlet to actually just pass the combined steps and trigs, and I guess the rotation, why not, as a list. And then we'll join that up with our sequencer ID. And we want that list to get sent through when it gets new sequencer data. So if I go back to 1 here and then I say 8, 3, and by the way, in the next video, we'll talk more about how we can save the parameters associated with each of these sequences in a better way, because there is a better way using pattr. So we will talk about that, but that's not what we're doing today. So now for number 2, I'll do 8, 5, and for number 3, I'll do 8. Let's do 9, 5 maybe, or 11, 5. How about? And if we come in here, we can see that we now have the configuration for each of those sequences stored here in the call. So what we can then do is, anytime that we change the poly mode, what we will want to do is dump the contents of this call. And we're going to want to get so when we do that, we're going to just get all of these items that are in the call emitted one after the other. So from the first outlet, the leftmost outlet, we'll get 830, then 835, then 1150. So we're going to just take the first item there. And actually, I'm just kind of doing this in real time here. So let's first check and say, all right, so if we want poly meter, so if this is equal to 1, then dump it. And join that with, and again, it triggers one. Actually, no. mc.target, mc.target, and prepend div. So if we get polymeter, so 1 here, we're going to dump the contents of, I'm sorry, if we get polyrhythm 1, we'll dump the contents of the call. We'll get the number of the length and steps of each of those sequences. We'll also get the identifier of that sequence from this rightmost, or this second inlet. And then that will cause us to send a message, which looks like this for each of those sequences into mc.subdiv, which will then change the granularity. So if we do, let's do as an example for number 4, let's do like 12, 12. And then for 5, we'll do maybe 4, 4. And we can kind of see what the result of that is going to be. So now we can see, once we toggled that button there, that the size of these steps on this 5th channel got way longer. Whereas on the 4th channel, they're shorter because there's 12 of them. Whereas if we then, for 0, we're just going to want to send this subdivision value. So I'm just going to actually store that. And I'm realizing I have a small mistake here. In fact, let's just do this. It's much simpler. And this needs to be connected here. Cool. and we will do prepend div here. So if we get 0, we're just going to send a simple div, whatever the subdivision is, because we want that just to apply globally, because that's what the poly meter is in the case of 0. And I apologize if during this discussion I've mixed up those two names. Hopefully you're following. One other thing that we need to do is if we change settings while we're in poly rhythmic mode, then we also need to re-dump things. So what I'll do is I'll just add a gate, and we just connect the outlet here, and we'll actually let's do it here, because we know that the Euclidean generator is going to first send the parameters onto the call, and then it will actually compute the sequence. So we know that this left inlet is going to come out after this right one, and then we'll just do a TB here. So now basically, if we have poly mode 1, which is polyrhythmic, then anytime the sequencer changes, it's going to redump the call and update the div parameter for each of those sequences. Beautiful. So let's try to have some semblance of cleaning up here. One thing that we can definitely do is just reuse the same mc.target object. We don't have to have two of them, which I suppose is debatable whether that's actually cleaner, but we'll do it. So we'll call this poly mode. And down here, we can call this one. Actually, let's just put this in poly mode too, because it's kind of related. Why not? Great. I would probably spend a little time making this slightly more beautiful at some point, but for now, I think that's probably good. Okay. So the next question now is, well, how do we actually send MIDI out or do anything with this pattern, right? We understand, we've seen a few examples about how we can actually use these sounds to trigger, or use these sequences to trigger sounds, and particularly one other video, which I'll put up in the corner there. But when we're doing this MC, it's a little bit more complicated. And I think, you know, one thing I've found is really fun to do with these multi-track sequencers is basically just to assign a single MIDI note value to each of the channels and have each of those patterns just fire a single note. And from that, you can get these kind of interesting evolving melodies. Or if you're sending the MIDI to something like a drum machine or a drum rack, which assigns different sounds to different MIDI notes, then you can actually get different sounds from those different MIDI note values. So what we'll do is create we'll use stash, like we have a bunch for this type of use case in the past, and we'll use mc.stash at mode 1, which is the index mode. And we will create a multi-slider. Size is 8 because we have 8 channels. And we'll do a range of, let's say, 36 to, I don't know, 57. Maybe it should have been 59, whatever. So we'll store those values there. And then what we can do is use mc.list. And basically what we want to do is get these sequences to send a value in here that is just the index of the sequence. So whether if it's channel 1, we just want anytime this fires, it to send 1 into the mc.stash. So what we can do is just say, you know, we can use mc.greater than here, which will turn these ramps into just square signals, and then multiply that by this value coming out of mc.list, which is just going to be 1, 2, 3, 4, 5, 6, 7, 8. And pass that into mc.stash. And I'm also going to pre-pend the sequence or the values that we get from the multi-slider with 0, because we're starting from 1. And I need to turn this to MC. We're starting from 1 rather than from 0. So when we actually look up from the stash object, we want this first item to be 1. And if that worked, oops, this is going to the wrong place. It needs to go here. It needs to go here. Wait, here. Okay. And let's turn this into integer mode. Okay. And we can monitor what we're actually getting. So we have 48, 40, 51, 45. So we could say we get 48, 48, 51, 51, 45. Great. So that's the first step. We've actually assigned nodes to each of those channels. And then the next thing that we'll do is use mc.midi player, which we talked about also in another video. We're going to send that note number value into the second inlet, and we're going to send the ramp from mc.subdiv into the first inlet, which will actually trigger our sounds. And we can use this default duration attribute of mc.midway player to basically set how long that note's going to be. So if I say 0.5, the note on event will begin when it starts receiving one of these ramps from subdiv, and the note off event will happen when that ramp gets to the value of 0.5. So the standard way to use mc.midi player is to connect it to a VST tilde object. But that's actually not what we're going to do today. Instead, we're going to make use of this write outlet, which is used for a MIDI event. And let's just print that result and see what it gives us. So we can see here we're getting 144, 48, 102, 128, 48, 0, all these values. What exactly are these? I know now that MIDI format, which is an object that we would very commonly use with MIDI out, connected like this, also outputs this MIDI event message. So we can look at the help patch to understand a little bit more what this MIDI event thing is. So it says, rightmost outlet of the MIDI format object converts MIDI input into properly formatted MIDI event messages for use with the VST tilde object. So the standard use for this actually is to pass messages into VST tilde. So I suppose, if we wanted to not use this kind of fancy secret connection that mc.midi player is able to use, we could probably do this, and it would actually work as well. Although I don't know why we would want to. However, we can see that this MIDI event message looks quite a bit like the message that comes out of the leftmost outlet of MIDI format. So if I clear my console and I send a note off, I could see I get 144, 60, 127 from the left outlet as separate messages, which is quite similar to what we get from this MIDI event outlet, where it's the same thing, but it's just packed into one list, prepended by the word MIDI event. So in order to basically to convert this MIDI event message into a regular MIDI message, it would appear that all we have to do is say route MIDI event, and then iter. And if I print this result, indeed. So I could even do this, and you can hear that nice piano, and that works. Great. So now that we know that that works, don't save. let's try it. So route MIDI event, iter, connect it to MIDI out, and we're going to send it to from max 2, which is what I have my my Ableton track listening to. And I'm going to play. And we're only getting one pitch. And that's because we're actually getting data on multiple MIDI channels here. So if I, in Ableton, start listening on all channels instead of just on channel 1, then I start to actually get all of my channels passing through and I get my melody. And that's because if we go back again and we look and we just print the output of MC.MIDI player's right outlet here, we can see we're getting 144, 145, 146, 128, 128. So what MIDI player does is actually it maps MIDI channel or MC channels to MIDI channels. So any data that it gets on MC channel 1, it's going to send on MIDI channel 1, on MC channel 2, on MIDI channel 2, and so on and so forth. So what we have here works because we have told the Ableton device to just listen on all channels and play anything it gets on any channel. But if you wanted to be able to use those channels for other purposes, you might want to just force everything to MIDI channel 1, because if I were to send all this same data on MIDI channel 1, this instrument would have no trouble playing it back. So let's understand a little bit better what these numbers mean. 144, 145, 146. We can see that the next two numbers, like 48 and 102, this is the note and velocity, right? Because we know that on channel 1, the note number is 48. And if we go into our MIDI, MC.MIDI player settings, the default velocity is 80, which doesn't match up with 102. But I also know that MC.MIDI player has this vel curve attribute that actually scales the velocity. So if I set this to 0 and I start to send MIDI again, you can see I'm getting a velocity. You might not be able to see that because I think my head is probably covering it, but I'll fix that. Down here, we're getting a value of 80. So if we go to the web and we look at this MIDI.org specification, MIDI association specification, we can see that this first byte value, 128, is channel 1 node off. And all the next ones up to 143 are also node offs for all the different channels. And the same goes for the node ons, 144 through to 159. So basically, these numbers, 144, 145, 146, those are node on events for channel 1, 2, and 3, respectively. And then 128, 129, and 130 are node off events for 1, 2, and 3, respectively. So all we really need to do, basically, is say if the value that comes through is greater or equal to than 144, then just send 144. If it's less than or equal to, or if it's less than 144, then just send 128. So we're going to do this. We will slice. It looks like I have caps lock on. There we go. After the MIDI event. So at this point, I'm getting this list of the 3 numbers. And I could use an expr. And I could say, is I1 greater than or equal to 144? If so, multiply that by 16 and add 128. And the result of this is that if I1 is greater than or equal to 144, then we'll get 1 inside these parentheses, times 16 plus 128 is going to give us 144. If I1 is less than 144, then this will return 0, times 16 is 0, plus 128 is the node off for channel 1. And then we're simply going to join that back with our note and velocity pair, and then pass it into the iter. So now if I play and I go to live, you can see we're getting all that same data on channel 1. And I can make one additional improvement, which is to allow us to control the MIDI channel. So if I say I2 plus 127, and then I connect a message box here for the MIDI channel, and I send 1, then I have some control of that. And let's just do a load mess 1 here, so that when the patch loads, it's set to send on 1. So let's try it. Great. And we can see all that data is coming through on channel 1. Cool. So that's it. So today we converted our single channel Euclidean sequencer into a multi-channel sequencer using MC. And we sent MIDI out to Ableton Live. You could also send it to any other device using a combination of MC.MIDI player and a little bit of extra max patching. Next time, what we will do is develop the user interface a little bit, talk about just how to make this look a little bit nicer, and particularly focus on how do we hook up the pattr system to all of these parameters so that we have control over everything, and so that we can actually save presets and cues and those sorts of things. Because we've talked a lot about how to build these sequencing systems. If you take that knowledge and start to develop instruments, you're going to find that you're going to want to be able to save things. You're going to want to be able to save presets. If you have a cool idea, you're going to want to save that. So we'll talk about how to do those kinds of things. But until then, happy patching, and I'll see you next time.